Hearty welcome to the Math Revision Made Meticulous video series. Topic linear programming. At this video, let us see some graphical method of solutions to LPP. Revision, as the name suggests, means looking back over previously learned information, ensuring that it is clear and fresh in the mind. 5 questions per video from selected topic is presented at this video series. The steps in answers are supported by the ideas used for getting the answer. Let us see what do you mean by linear programming. Linear programming is a method for determining optimum values, maximum or minimum, of a linear function subject to conditions expressed in linear equations. The linear equation Z is equal to a1x1 plus a2x2 plus and so on to an xn, which to be optimized, either to be maximized or minimized, is called objective function, because this is our objective, either maximization or minimization. And the inequations or equations on the variables of a linear programming problem are called constraints. Therefore, objective function plus constraint put together form a linear programming problem. We are going to solve the objective function based on the given constraints. Let us see what do you mean by feasible region. A common region determined by all the constraints of the linear programming problem is called the feasible region. A problem may have 2 constraints, 3 constraints or 4 constraints. We are going to get a common region. And a feasible solution which maximizes or minimizes the objective function is called an optimal solution. Therefore, all the points in the common region will be solutions, but out of them there will be one solution which will maximize or minimum, not 2 maybe. The objective function is called optimal solution. Let us see the graphical method of solving linear programming problem. Let me take a objective function which is a linear equation in 2 variables, that is Z is equal to ax plus by, and let me consider that the feasible region is a bounded region. It's an optimal value subject to the constraint described by the linear equation. The optimal value must occur at the corner points of the feasible region. Suppose if it is a bounded region, the optimal value, whether it is maxima or minima, will be at the corner points or the vertices. I am just showing you a bounded region now, and you are seeing over here the corner points 0, 8, 4, 10, 6, 8, 6, 5, 5, 0 and 0, 0. Now remember, all the points of this region are solutions, but we want optimal solution, feasible optimal solution, where it will occur only at the corners. You have to check only the corner points and you will get the answer. Sometime what will happen, you may get the region as an unbounded region. In that case also, the optimal value must occur at the corner point. I am showing you a figure. Here the common region is an unbounded region, where A, B, C, D, they are all the corner points of the unbounded region. We are going to find the value of the objective function at these points, and that will be the optimal value. Either it may be maximum or minimum. And now before you go for that, we have to understand the solution of linear inequation. Suppose if you have linear equation which you studied in lower class, suppose if you have the solution for ax plus by is equal to c, it will be the set of all points lying on the line. Suppose I am taking a line x plus y is equal to 5. What are the solutions now? The solutions are all points lying on it. For example, minus 2, 7, 0, 5, 2, 3, 3, 2, 5, 0. I am just showing only 5 points to you. But all the points, infinite number of points lying on the line, they are all solutions. Now let us consider what will be the solution for this linear inequation. It will be set of all points lying on the half plane. The line will divide the whole plane into 2 half planes. In one half plane, the solution will be there. And if it is greater than or equal to 0, it excludes the origin. For example, the same equation I am taking, x plus y greater than or equal to 5. Now you are seeing x plus y is equal to 5, only solution lying on the line, points lying on the line is the solution. But x plus y greater than or equal to 5, all the points lying above the line. 0, 0 is not satisfying this equation, therefore origin excluded. Let us go to the next equation, ax plus b less than or equal to c. Once again, it is the set of all points lying in the off plane, including the origin and the points on the line also. Now you are taking the same equation, x plus y less than or equal to 5, x plus y greater than or equal to 5 above the line, x plus y less than or equal to 5 below the line. But how we are deciding that above or below? Checking whether origin is satisfying the equation or not. Very simple. Now the solution of the off plane, suppose all of you now we have seen that, sir, if our origin substitute satisfies, I will take the including the origin, not satisfy, I will exclude the origin. But what will happen if it passes through the origin? It will be decided by verifying the region in which the points satisfy the inequation. For example, I am taking this x plus y greater than or equal to 0. It is passing through the origin and it divides it into two halves, one in the top, one at the bottom. Whether top will come or bottom will come, very easy. Take any point in one of the region, either the top one or the bottom one, above the line. Let me take the point, for example, 2, 2. Now 2 plus 2 is definitely greater than or equal to 0, that will come. Suppose you take a point at the below, for example, minus 4, minus 1, it will not satisfy. Minus 4 minus 1 is not greater than or equal to 0. For we have to take that region, a point, set of all point which is satisfy this equation, that region you have to take. Let me take one more example. I will take x plus y less than or equal to 0. Here the points, for example, if you take 3, 1, not satisfying. Suppose you take 5, 4, it is not satisfying. Therefore, all the points which are lying below the line satisfy. Therefore, that is the solution for this linear inequation. Well, graphical solution, what you have to do? Consider the given constraint as equation and draw the respective lines. Decide the solution half plane by checking whether the origin is included or not. If the line passes through the origin, decide the region by checking the points satisfying the region. Identify the feasible region and the corner points. It may be bounded or unbounded. And calculate the value of the objective function at these points and find the optimal value. If they ask the maximum, take maximum. If they are the minimum, take the minimum. Sometimes remember, optimal value may occur at more than one point. Okay. Let us take one question now. Solve the following linear equation. Maximize and minimize. Sometimes they may ask both the values. 60x plus 15y, subject to the constraint x plus y less than or equal to 50, 3x plus y less than or equal to 90, and x comma y greater than or equal to 0. This x comma y greater than or equal to 0 will be a common condition in all the problem, because all problems are practical problem. Therefore, we want it to be in the first quadrant only. Well, now I will take the constraint x plus y less than or equal to 50. In lower class, you have found the points of x and y and drawn. The easiest method is put y is equal to 0, get the value of x. Put x is equal to 0, get the value of y. You are getting the points on the x-axis and y-axis and join it. For example, I take the points now 50, 0 and 0, 50, and I am writing that whether origin is included or not. Yes, it is included because origin is satisfied by this equation. Let me take the other one, 3x plus y less than or equal to 90. When I put y is equal to 0, x is 30. And when I put x is equal to 0, y is 90. Therefore, I am getting the points and origin is included because origin satisfies. Now, x comma y greater than or equal to 0 tells me that the feasible solution is in the first quadrant. Let me try to draw the diagram now. First, let me take x plus y less than or equal to 50. These are the points and origin included. This is the solution. Very simple. Downwards, that is, it will go down because origin is at the bottom. Origin is not at the top. Let me go to the second line now. In the same graph, I will draw this 30, 0 and 0, 90. Now, I am getting that another color I have shown you. Here also origin is included. Now you are very well seeing that in the first quadrant, which is the region common to both the solutions. Now this is the region common to both. Therefore, OABC is the bounded feasible region. Now what you have to do now? You have to find the vertices of this OABC. Now these are the vertices OABC. Now this is the optimal value lies at the corner points. What you have to do now? You have to check the value of Z at these points. I am just checking now. I am checking at 0, 0, this value is 0. At 30, 0, it is 1800. And 20, 30, it is 1650. 0, 50, it is 750. Be careful in this problem, they want both maximum and minimum. Which is maximum? 1800. And which is minimum? It is 0 at 0, 0. Over. Okay. Now let us go to the next question. Here we have to simply maximize, no minimization. 2x plus 3y greater than or equal to 100, x plus 2y less than or equal to 80, x greater than or equal to 14, y greater than or equal to 16. 4 constraints. Let us take the first constraint. Put x is equal to 0, get the value of y. Put y is equal to 0, get the value of x. Suppose if you are getting some 100 by 3 like that, you can take some convenient value. Now the points are 50, 0, 20, 20. 20, 20 satisfy that equation. Okay, origin not included. The second constraint, the points are 80, 0, 0, 40. The same idea I have applied. Here origin included because it is less than or equal to 80. Now the constraint is x greater than or equal to 14. What is it? It is a straight line passing through the point 14, 0 and parallel to y axis. Origin not included because x is greater than or equal to 14. y greater than or equal to 16, once again passing through 0, 16, and it is parallel to x-axis and origin not included. X, y greater than or equal to 0 means the feasible solution is in the first quadrant. Now let us try to draw these lines now. 2x plus y greater than or equal to 100. These are the points. Origin not included. Yes, I got the top portion. Go to the second constraint. X plus y less than or equal to 80. These are the points. Origin included. Therefore it comes down. Again I am taking the third one. X greater than or equal to 14. Passing through 14, 0 parallel to y axis. This is the line. And origin not included. Therefore it goes outside. That is away from it. Away from the origin. Go to the last constraint, y greater than or equal to 16, passing through 0, 16, parallel to x-axis, origin not included. Now, you are seeing that what is the region being formed in the first quadrant. This is the region, A, B, C, D, being formed by all the 4 lines, where A, B, C, D is the bounded feasible region. Now, we have to get the coordinates. You can get it from the diagram directly, or you can solve the equations and you can get it. And these are the optimal value lies at the corners, and I am getting those values now. And as usual I am getting the value of 20x plus 30y at these points. This is the problem of maximization. Therefore maximum value is 48, 16 obtained at 48, 16 1440. Now move on to the third question. Solve the linear equation graphically. Minimize z is equal to 3x plus 9y, x plus 3y less than or equal to 60, x plus y greater than or equal to 10, x less than or equal to y. Good. Constraint first constraint, x plus 3y less than or equal to 60. These are the points. Origin included. Second one greater than or equal to 10. These are the points. Origin not included. Now this is x less than or equal to y means x minus y less than or equal to 0. Passes through the origin. And the region contains the point 10, minus 10 and 20, minus 20. Only these 2 points satisfy the equation. Let us see. X, y greater than or equal to 0 means the feasible solution is in the first quadrant. Well, the constraint is x plus 3y less than or equal to 60. The points are 60, 0, 0, 20. Origin included. I have drawn it. Second constraint 10, 0, 0, 10. Origin not included. It goes up. Third one, passing through the origin and the region should contain 10, minus 10 and 20, minus 20. Therefore, it goes up. It is not containing 20, 10 and 20, 20. It is not containing. Be careful with that. Okay, well. Okay, well. Therefore, ABCD is the bounded region which is very close to the y-axis. We want the coordinates. It is obtained from the diagram itself. 5, 5. 15, 15, 0, 20 and 0, 10. I have just taken in anti-clockwise direction. This is the optimal value. I am finding the value of the objective function given 3x plus 9y at these points, and you are checking out that the minimum value you have to find, it is 60 at 5, 5. Over. Therefore, minimum value is 60 at 5, 5. Let us go to the next question. Once again I have taken a question where it passes one of the straight line passes through the origin. Minimize x plus 2y, x plus 2y greater than or equal to 100, 2x minus y less than or equal to 10, 2x plus y less than or equal to 200. First constraint, points I have found, origin not included. Second constraint, points I have found, origin, it passes through the origin and 20, 60 lies in the region, and 2x plus y less than or equal to 20. These are the points, origin included. Now, after getting these points, now you keep it in mind that how to take the scale on the x-axis and y-axis. Here I have 100, 50, 200 like that. Therefore, you have to take, based on that, you have to fix the x-axis point. For example, 20, 40, 60 you can take, or 10, 20, 50, 100, 150 you can take. Accordingly, you have to take. And x, y greater than or equal to 0, you know what is the meaning. Feasible solution is in the first quadrant. Let me take the first constraint, x plus 2y greater than or equal to 100. These are the points. Origin not included. Good. I have taken 20, 40 in the x-axis and 20, 40 in the y-axis also. Taking the next constraint, it passes through the origin, and 20,60 lies in the region. When I put 20, 2 into 20 is 40, 40 minus 60 is less than 0. Therefore, you are getting 20,60. Where is it? It is in the top one. Therefore, you have to take the top region. You can take any other point and then check whether that point lies in the region or not, either the bottom one or the top one. Well, let us go to the third constraint, 2x plus y less than or equal to 200. These are the points, origin included. Therefore, I have drawn it, the point 100, 0 and 0, 200, and origin included, therefore it goes down. Good. Let us see what is the common region now. The common region is ABCD, which is a quadrilateral. This is the feasible region. This is very, very important. You have to identify the feasible region. Then only you can get the corners. I can get the corner points now. 0, 50, 20, 40, 50, 100 and 0, 200. Therefore, at these points only I am going to get the feasible solution. Okay, now I am getting the corner points now, and I am checking the value of z x plus 2y at these points. And this point is a problem of maxima. Maximum is obtained at 50, 100. The maximum value is 400. The maximum value is 400. Well, let us go to the next question. Solve the linear programming problem graphically. Minimize z is equal to, subject to the constraint, x plus 2y greater than or equal to 10, x plus y greater than or equal to 6, 3x plus y greater than or equal to 8. As usual, I will take the first constraint. Points I have obtained, origin not included. Second constraint, I have get the points, origin not included. Third one, I have taken the constraint, origin not included. Let us take the condition that x comma y greater than or equal to 0. Feasible solution is in the first quadrant. The constraints are x plus 2y greater than or equal to 10. Points I have put, origin not included. Good. Let us go to the second one. X plus y greater than or equal to 6. Origin not included. It goes up. Again, third constraint 1, 5, 0, 8. Origin not included. Now, you got the corner points of a unbounded region. The feasible region is the unbounded region ABCD. Now also we had one theorem. Optimal value lies only at ABCD. The corner points only. Therefore, the corner points are 0, 8, 1, 5, 2, 4, 10, 0. Now, the corner points we are finding the value of z at these points. I am getting 80, 56, 52, 60. This is the problem of minimization. Therefore, it is obtained at 2, 4, which is 52. But remember, as it is the minimum value, as the region is unbounded, there may be some other value which may be minimum than this 52. We have to check it. Further, there is one method to check it. What you have to do is, you consider 6x plus 10y less than 52. Why I am taking this 52? Because 52 is my minimum value. You take this xx plus 10y less than that minimum value which you have calculated. You check whether any point. For example, I take 10, 2. Where is 10, 2? You are just seeing that 10, 2 is in the unbounded region which we are taking. You take a point in the unbounded region and check whether it is satisfied by its equation. For example, when I put 10, 2, it is 60 plus 10y, therefore it is not less than 52. Therefore, if it is happening like that, definitely the value which you have obtained does not have a common point, therefore this is the minimum value. Suppose if it have any common point there, then all of you know that so many minimum values will be there, or this may not be the minimum value. It can have other value, maybe another maximum like that. Therefore, you check whether the given constraint, that is objective function, less than or greater than the minimum or maximum value which you obtain. Check whether it is satisfied. 100% will get satisfied, no issue. Therefore, the minimum value is 52. Success is dependent on the efforts. All the best. Thank you, friends.